Hey students, I thought I'd make another little video here. Again, very tough problem. It's from chapter 23. It's from the hard book, the University Physics, chapter 13, volume 2, number 80. And it has these three resistors that are kind of set in a big rectangle and two small squares here. And it says this: two infinitely solenoids cross the plane in the circuit as shown below. Now, they don't really show these solenoids. The solenoids, let's see if I can get some kind of demonstration here. I like to kind of use this little spring as a solenoid. But if the solenoid was angled like this so it comes in and out of the plane of the paper, and here's the second one, there would be a magnetic field that would go along the axis. Now, of course, it depends what direction the current is set up. And so the little dots are saying that the magnetic field, I'll take my right-hand rule, would be pointing out, where here, the solenoid, get my thumb pointing in, the current would have to be in this direction. And they don't even show that in the picture, and it's probably best they don't, because we've got enough going on. All we need to realize here is that, let's see, there are some solenoids that have a radius that are, and it looks like a 0.1 meters and a 0.2 meters respectively. And the current in each solenoid is changing such that the field changes at a rate of 50 teslas per second. All right, then the question: what are the currents in each of these resistors? So there would be a current, there'd also be a direction. Maybe we should talk about that a little bit later. They don't ask for it. But this problem is a lot like number 79. I don't know if you got a chance to watch my video on number 79, but it might be worth watching. I do think it's a little bit easier. Of course, I think so does your author. He color codes it blue for a hard one and black for a little easier. Either way, it's still hard. I don't want to call this one easy in any fashion, but it is a bit easier. And so let me use some of the results from 79 on 80 here, because one of the things we talked about in 79 is that there is a current if you have a voltage and a resistor. And when you first look at this, you don't see any batteries, but I am going to point out that voltage equals, or current equals voltage divided by resistance, Ohm's law. We're probably going to do Kirchhoff's laws for this one, which is an extension of Ohm's law. So let me write Ohm's law in this fashion. But the key, though, is we have to recognize that there's some voltage somewhere. And way back when we did, batteries, which I guess is chapter 20, it made sense. I guess 20 and 21, we put a battery in there, and we had a chemical reaction that supplied the voltage. But now our voltage is coming from someplace a little different, and that's where this chapter comes in. An EMF exists if there is a change in flux. And so this, again, makes sense, the key to this chapter. This is the fundamental idea. This is Faraday's law, and Faraday's law explains many, many, many things. And so that's the good news. In one sense, you'd say the chapter's pretty easy. It's just this one main idea. But the other part of it is we've got to put past chapters together, and you heard me say that on number 79 quite a bit. And so I'm going to do that also here. We're going to need this stuff from 20 and 21. We're also going to need that. I was going to think we needed the solenoid, but we probably don't. Let me just put the flux as BA, which we can use if the flux is uniform, and it is for a solenoid. And this is why I would say I believe this problem is a little bit easier than 79. If you looked at 79, when I went to calculate the flux on number 79, I had to chop the rectangle into little slices and add up an infinite number of slices, which bring up the calculus of an integration in order to eventually get the total flux in number 79. We don't have to do that for this problem. This problem has a nice uniform field. So there is no requirement to do any calculus here, at least on that level. And if you remember from 79, there was 2 steps of calculus. The first one we see on page 1, where we add up all the flux and we have to do an integral, and then a derivative when we have to do Faraday's law. And that one we're still going to do, because when I go to write delta flux over delta t, I might write it in its calculus form, that is, in the limit as delta t goes to 0 of delta flux over delta time, and write it as d flux dt. And I say that because when I put this in there, I could then say this is the derivative of BA. And the area does not change. So we can replace, or maybe I shouldn't say replace, but move the area out in front, anything that doesn't change, because our calculus are linear operators, we can pull in front. And then this would be then the area, and they directly give the derivative of the magnetic field at a value of 50. And so I will just substitute in dB dt. And so mathematically that's not real hard, but conceptually it might be, because we're really studying the math. We're really reading the math. We're really saying, what does flux mean? What does the calculus of a derivative mean here? And we were able to then say that this is the change in flux with time, and that is the EMF, that is the voltage. Now, we also might want to pause for a moment and say, well, what areas are we talking about? Because we have a couple of areas here. I mean, we have this area of solenoid number 1. You might even say we have the area of rectangular or squared, top square. And we have area of solenoid number 2. I put my solenoid back in here. But we also have the area of that bottom square. And I suppose we also have the area of the big rectangle. And going back to the meaning of this area is really the area of where there is a uniform magnetic field. So looking at solenoid number 1, I could get the voltage produced, and I'll put a little number 1 here, by saying it is the area of that solenoid. And that solenoid then has an area of pi r squared. And that's 0.1 squared, and then times the 50. Whereas the EMF, or the voltage of solenoid number 2, would again be the area of where there is flux. Okay, and so this would be pi, and the radius is 0.2 squared times 50. So that's double the radius, or 4 times more. So if I grab my calculator and go pi, and multiply by 0.1 squared, and multiply that by 50, I get 1.57 volts. And the second one would just be 4 times bigger, so I'll save a little bit of calculator work and just multiply by 4. And so that would be 6.2 volts. And let me put a little box around that, because that is the work needed in connection with this chapter. Well, not quite done. I do have a directional issue that I've got to deal with. But here's what I'm saying by that. Let me redraw this now as a circuit and look like something from chapter 21 here. I've got a 4 ohm resistor across the top. And I've got an 8 ohm resistor in the middle section, and I got another 4 ohm resistor down at the bottom. Now I'm not going to close up this, because here is kind of my thinking. In the real picture, I just have a wire here, and so part of me wants to just connect them. But what I'm going to do is get rid of the magnetic field and replace it with the voltage. So I'm going to put a battery right here. So I'm going to put a battery that is equal to 1.57 volts. That would be perfect for a AA or AAA or C or D battery. These single cell batteries are 1.57 volts. Okay? But I shouldn't have said that, because these aren't batteries. These are coming from the change in the magnetic field, which the magnetic field is coming from a solenoid, and so there would be some changing currents in this solenoid, not really shown in the picture, that induces the change in flux, which then induces a current in here. I paused here because I'm not sure which side to make the battery positive and negative for a moment, and then that's where Lenz's law comes into place. Again, more parts from chapter 23, and a hard part. So if I read this right, they say, and the current in each solenoid is changing such that the field, and I think they're talking about the field strength, not the direction, is increasing by 50. So the field is already pointing towards you guys on the screen. And so it's just going to get bigger and bigger and bigger. And so what that means is more and more flux is coming towards you. And remember, Faraday's law says that the current is set up in this loop. And I'm just kind of ignoring this one for a second. Current would be set up in this loop in such a way that it would oppose the change. Okay, so as the flux is coming out more and more and more, because it's increasing by 50 Teslas every second, the current is going to be set up either counterclockwise or clockwise, such that it opposes the change. In other words, keep it back where it was. And so it's going to want its flux, what I call the secondary flux, going in to counterbalance this increased flux from that solenoid. So if I point my thumb going in for the flux, I can see that this wants to make current go around in a clockwise direction. If you only had this top piece, that's what would happen, that the current would go around this way. Now, that means this right here is equivalent to a battery where this is positive and this is negative, and so that's what I'm going to put in my diagram. I'm going to put a positive here and a negative there. And so the current wants to wrap around in this direction. And maybe I should call it current number 1 to go with voltage number 1. And so you can see, the hard part of this problem was not only to find out how much voltage it was, but what direction is it. And we can do that same logic for the bottom rectangle. So the bottom rectangle has a lot of flux going down, and then it's just getting more and more and more down. And so Lenz's law says the flux, the induced flux, that is the flux created from this bottom rectangle, whether it be clockwise or counterclockwise, wants to oppose the change. And since more is going down, it wants to go up. And if I point my thumb up or at the screen, it's going to wrap around in this direction, call it number 2. And that would be done if this was thought of as a battery where this is plus and this is minus. And so I got a battery here that's plus and a battery here that's minus. And probably not a big surprise that the batteries are opposite of each other. You can kind of see that because the magnetic fields are opposite of each other. And you kind of saw that coming. All right. And of course, this voltage is 6.28 volts. And I should have wrote this 1.57. And that is the, well, I think we still got some hard stuff to do. But that is the stuff that is not only hard, but it's the stuff connected to this chapter, chapter 23. Okay. And now I can really go back to chapter 20 and 21, Kirchhoff's laws. And so if I call this number 2, number 2 would loop up, and they would meet at this node. And so as current number 2 comes in and current number 1 wraps around, they're going to join at this node and go across the resistor number 8, I would call it current number 3. And so we have 3 unknowns, current 1, current 2, and current 3. And as you remember back there, we said we should do a loop of the 2 small ones. And the big one does not give us an independent one. And then we would have the node, and I'll just do the node first. So what comes in, what we call conservation of charge, current 1 and current 2, makes current 3. And so maybe I will refer to that as equation number 1. Now, equation number 2 would be this loop. And maybe I'll start right here and just remind you the loop, we can go around the loop, but the sum of all the voltages have to be 0. It doesn't matter which way you go, it doesn't matter where you start. So I'm going to start here and go clockwise. And so from the negative to a positive is an increase of plus 1.57. Going with current number 3 would be a decrease of 8I3, and going with current number 1 would be a decrease of 4I1, and then that gets us back where we started, and so that equals 0, and I'll call that equation number 2. I'm going to do the same thing for this bottom loop, and so again I can start anywhere and go either direction, so I just like to do the negative side on the battery here. So I'm going to go ahead and go from here to here, so this is a plus 6.28. This is with the current in number 3, so it's a negative, and it's this Ohm's law that I mentioned earlier. This is the thing we need to grab from chapter 20. And then again, we're with the current, so minus 4I2 is equal to 0, and that's equation number 3. And so now we got some work ahead of us. We need to start eliminating variables. And maybe the first thing to do is to recognize that this first equation is already solved for I3. So why don't we take equation number 1, and everywhere we see an I3 in the next 2 equations, we will put that in. And then that means we will have used equation 1, and we will not have the variable I3 anymore in our equation. So this would look like this. We would have 1.57 minus 8 times I1 plus I2 minus 4I1 equals 0. And the other equation would be something like 6.28 minus 8 I1 plus I2 minus 4I2 equals 0. Yay! Okay. Actually, now that I just see that, I see a shorter way to solve this one. But since I started down this road, let me keep going. So I'll say it again. We have a system of equations right here, 3 equations, 3 unknowns. And the first step is to eliminate one of the variables. So I did, I3. And of course, now you only have 2 equations to work with. Let me simplify these 2 equations, so nothing real fancy here. 1.57. And when you do a distributive property, you can see here that there's an 8 and a 4. And 8 and a 4 make minus 12i1. And minus 8i2 equals 0. And then over here, now, yeah, I wish I would have done this a little different, be shorter. But this is more, I think, straightforward. Harder, but straightforward to see. So I'll keep going. But anyways, this is minus a, and you can see right here, this would be an 8i1. And then this minus 8 with this minus 4 makes minus 12i2 equals 0. So again, I still have the same 2 unknowns that I had back here, which is I1 and I2. I just kind of simplified it because now I want to eliminate, and you can decide which one you want to eliminate. I think what I'll do is eliminate I2, and maybe I'll try a little different method. Why don't I just take this equation, and before I do anything, multiply everything by 1.5. And I won't touch the bottom one, but if I take the 1.57 and multiply it by 1.5, you will get 2.36 minus, if I go 1.5, that'll be 18. But this was the big one, because if I do 1.5 here, this becomes minus 12i2 equals 0. And let me just copy down the second equation. And now you can probably see mathematically, you probably called this the elimination method in your algebra class. But what's really nice then is these 2 equations. Now, if they subtract, the I2 goes away. And of course, you could have also have just solve this for I2 and do a substitution. But sometimes substitution is really hard and long, and elimination is a little shorter than that. In fact, there was a better elimination earlier on that still kicking myself for not going that direction first. But it's probably good for you to see the more direct route. Okay, so as I subtract things, this would be right here, the first equation minus the second, 2.36 minus 6.28. It's going to give me negative 3.92. And here, a minus 18 minus a negative, so that would be a plus, gives me minus 10i1. And this is the big one. Negative 12 minus another negative 12 is 0. And so now I've combined these 2 equations and have lost the variable I2. And now I'm down to 1 equation and 1 variable. So just to kind of remind you of your algebra, right? 3 equations, 3 unknowns. You combine them, get rid of 1 unknown, and 2 equations, 2 unknowns. Combine them, get rid of another unknown and another equation, and then you're finally down to 1 equation and 1 unknown. Then maybe I better call this page 1. Okay, so simplifying this, I will then say that I have negative 3.92 equals, I'm just going to move it to the other side. 10I1, or I1 is equal then to a negative 0.392. Now let's talk about the negative in a moment here, but let's finish the algebra. So once I've gotten I1, I can come back to any of these equations and put it in to get maybe I2. And maybe the thing to do is this equation. And so I will go 1.57 minus 12 times a negative 0.392 for the I1 minus 8I2 equals 0. And if I move the negative 8I2 to the other side, it becomes positive. And here, if I put together the 12 times the 0.392, and the two negatives make a positive, and I add that to the 1.57, I get the 6.27 there. And so now, if I divide that by the 8th, I get a positive 0.784 amps. And so now I get the second variable to my math. And again, the third variable, you kind of get the same way. Go back to any of these equations, and in this case, I'll probably go all the way back to here because I3 is just those two added together. So I will take the I2 and add to it the negative 0.329 and get 0.392. Yay! And I think I've technically got the answer, although it might be nice to make a mention about the negative, because going back here, my I2 is kind of along this loop. So I2 is then a 0.784, and that kind of makes sense. This is the bigger battery. This was the 6.28 volts going this way. And this battery, V1, V2, is V1 was a smaller battery, and it looks like it's getting overpowered. You see, I drew it as going this way, which is what it wants to do, and if it was all by itself, it would do, but sometimes the stronger battery can go in reverse, and that would be charging up the battery. That's what you do when you plug in your cell phone. You have your cell phone at about 3 volts, but you plug it into the USB plug, which is 5 volts, and it just rams current the other way than what it naturally wants to go. And that's what's happening here. So I'm going to change this and put a 4 ohm resistor and say the current then is a 0.392, and it is going then this right to left instead of left to right. And that's the negative of how we labeled it when we solved the problem. And I3 is this 8 ohm resistor, and it is a positive number, so it is going in the direction that we labeled, which would be here. And so the current would come up, hit this node, and split, and it looks like kind of a 50-50 split. Half of it would go through this battery and charge it up, and the other half would bleed off through this resistor. So we probably, some kind of fancy electronics to keep us from overcharging this battery. And as you can see, these 2 pages were a lot of work in itself, and it really had nothing to do with this chapter, which made it a long, hard problem. So hopefully this stuff here with Faraday's law and Lenz's law made sense. That's the new stuff. And then as we apply it to the old stuff with a lot of algebra, we get our answer. All right. Take care. Hope that helped.